Welcome back. Thanks for joining me today. What we're going to talk now is how do we solve problems for one-dimensional motion. After working through all of these labs and explorations of position versus time, velocity versus time, and acceleration versus time, our goal now is to put the pieces together and use it to predict any motion for something that moves in one direction and moves with constant acceleration. Let's go ahead and get started. First, what I want to do is just make sure we recap a few key things about acceleration. So the first thing to remember about acceleration is that it is a vector quantity. Remember that this term vector here means that we have magnitude and direction. So acceleration is something that has not just a number, right? How hard are you hitting the brakes? How hard are you hitting the gas? And what is your change in motion as a result? But there's a direction to it. Remember that the units are meters per seconds squared. So that comes from our equation, where so far what we've talked about is the average acceleration is equal to the change in velocity per some time interval. And so the units come from the change in velocity being meters per second divided by seconds. Think about how much do we change our velocity each second. A key thing to point out here is this word deceleration that people often use in everyday life is a really bad term because it makes it sound like there is something for slowing down versus something for speeding up. And that's not the case. Acceleration is always any time there is some change to our motion. So a change in motion can be if you're driving a car, and perhaps what you do is as the car is moving forward, that's your initial velocity, you hit the brakes, and so your acceleration is backwards, it's to the left, because your change in velocity will be to the left. Or it could be if we do a top-down perspective, thinking about sometimes all we need to do is not just change how fast we're going forwards or backwards, but if we started moving this way and you turned the car so that it moves that way. I'm changing the direction, so I am having a change to my velocity because it is a vector quantity. All right, so what we'll do is work through a few problems just focusing on acceleration to make sure we're good with that, and then we'll talk about how to solve these problems. First question, just to check if we're okay using the equation for acceleration, a cyclist starts from rest and experiences a constant acceleration of 2 meters per second squared. How fast will the cyclist be going after 6 seconds? So a few things to highlight, right? Anytime you see something like from rest, you want to make sure that you're comfortable noting that the initial velocity is 0 meters per second. Constant acceleration means that we don't have to worry about sort of the in-betweens of this motion, just the beginning and the end, and we're given a value for that acceleration. We're also given a time here. Right, so if the equation is that the average acceleration, and I'm always going to take the time to write average because we have to remember it's not instantaneous, that comes later with calculus. So remember that change in means final minus initial. So our initial is 0, and what we want is this final value. So I need to move time to the other side. So we have this acceleration times this change in time gives us v final. And we can see that it's just 2 times 6 equals 12 meters per second. And that's our answer for that question. All right, let's take a look at the next one. A cheetah creeps along at a pace of 2 meters per second for 2 seconds and then bursts to a maximum speed of 40 meters per second in 2 seconds. What is the cheetah's average acceleration? So I put this question in as something where I feel it help us first start to see why velocity time graphs are really important. From now on, what I want you to get in the habit of doing is anytime we have a problem, we want to model what is going on with the motion. So on this graph here, starts out at 2, and I know things aren't going to be to scale, and that's for 2 seconds. So the graph would start like this, and then the cheetah speeds up in another 2 seconds to 40, which with my scale, would be way up there. But the key thing is to then think about when we asked about average acceleration, what we are asking about is what is the slope from the very beginning of the graph to this, which is not the slope of that. Right? It is a different less steep slope. So to find that average acceleration, what I want to do here is find what is my change in velocity in some change in time. So the first mistake that could be made is you could write that this here is 40. That would be the first mistake that somebody could make. Instead, remember it's v final minus v initial, so that would be 40 minus 2. And then the time intervals were the other mistake could make. It really depends on the question, right? You could fairly argue that maybe the question needs to be more specific. If I wanted to know what is the acceleration just for this phase, then I would do this 38 divided by that time of 2 seconds. But if I sort of wanted to know what is the average acceleration for this whole motion, well, there are 2 seconds where there's no acceleration. So instead of doing 38 divided by 2, I would do 38 divided by that total time of 4. So we'd like a more specific question, but it just helps to illustrate the fact that we want to be careful about our assumptions, and oftentimes, especially on the College Board AP exams, they will be really tricky with the ways that they phrase things. And we want to be really careful about identifying what are some tricks that they might give us. So for this, what I would do is do the 38 meters per second divided by 4 seconds for my answer. Unless I was asked what is the cheetah's average acceleration from 2 to 4 seconds, in which case then it would be 38 divided by 2. Okay, let's take a look at the next one. Another question here to help us see the value of making velocity time graphs. If a sprinter starts from rest and experiences a constant acceleration of 5 meters per second squared, how far will he travel in the 1 second of the race? So if we make a velocity time graph, right, he starts from rest. So on this velocity, on this vertical axis, I need to start at 0 for that time of 0, and has a constant acceleration of 5. So that means that every second, our velocity should go up by 5. So we'll be at 5 in the first second, we'll be at 10 in the second, and we'll be at 3 in the third, or excuse me, 15 in the third. So the motion would look like that. We're asked how far does he travel in the first second. So the default answer that somebody might say is 5, because the final velocity at that 1 second, at t equals 1 second, will equal 5 meters per second. And we might think, okay, in 1 second then he goes 5 meters per second. But the key is, except at that 1 second, the velocity was always less than 5 meters per second. So the answer then needs to be less than 5 meters. And let's talk about, we mentioned briefly earlier that the area under here is the displacement. So the area of this is a triangle. It's 1/2. The base is that v final at 1 second. Or excuse me, the height is that v final at 1 second. And the base is that time interval. So I'm really taking half of that final velocity. So I'd be doing 1/2 of 5 meters per second. And that motion occurs for 1 second. And so really the person travels 2.5 meters. So careful with acceleration and displacement. It's a little bit trickier than we might expect. Now we've used the acceleration equation. Let's also make sure we're comfortable just sort of what this term acceleration means using this question. If a car experiences a constant acceleration of 8 meters per second squared starting from rest, what does that mean about the car's motion? So option A says it will move 8 meters every second. So that would be true if instead the velocity was equal to 8 meters per second and would require the acceleration to be equal to 0. As we just talked about, in the first second, the car, as it goes from 0 to 8 meters per second, will in fact travel 4 meters, so it's going to be less than that, so that's not true to begin with. And then how far it travels will change as the car goes faster and faster and faster. So point number 2 then says it will move an additional 8 meters more than what it did in the previous second, and then says that the first displacement will be 8, and that we just covered is not true again, right? We're only going to cover 4 meters. Now, let's think about what happens after the first second. So in the first second, we go up to 8. And then in the next second, we'll go up to 16, and then 24. So the graph would look something like this. Now, we already showed that in the first piece here, in the first second, we would go 4 meters, but we could still look and see, okay, how much further do we go in the second second? So in the second second, now we have this shape here that is neither a triangle nor a rectangle. It's a trapezoid. So the area of a trapezoid is 1/2, if you remember it, base 1 plus base 2 times height. Now the problem here is that the bases are actually the heights. So I'm going to rewrite this in terms of physics variables that are more helpful. It's 1/2 the initial velocity, or the velocity at 1 second, plus the velocity at 2 seconds, times the time interval. So for this second shape, I would have 1/2 times 8 plus 16 times the time of 1 second. All right, so 8 plus 16 is 24, divided by 2 is 12. So in the second second, we move another 12 meters. So notice that that's 8 meters more than the previous case. So B is almost onto something here. If we do the next one, right, we have another trapezoid. And this time we'd be doing 1/2 of V initial, or V at 2, plus V at 3, that V final of 24, times that change in time, which is 1 second. 16 plus 24 is 40, right? Divided by 2 is 20, times 1 second gives us 20 meters. So we go 8 meters more than in the last second. So technically we do move an additional 8 meters more than what it did in the previous second, but the problem is that we don't move 8 meters in the first second. For C, we're told its speed will increase 8 meters every second. That's true, right? That's the definition of acceleration. Can't be D, as we just showed there, that B isn't quite right. And then E, its speed will increase an additional 8 meters per second more than the previous second. So that can't be true. That would require our acceleration to not be constant, which is not the case here. All right, let's keep going. Quick conceptual check. A sprinter explodes off the starting block with an acceleration of 3 meters per second squared. After 4 seconds, her acceleration drops to 0. What happened? So again, really helpful to model this on a VT graph. For the first 4 seconds, 1, 2, 3, 4, we have a constant acceleration of 3. So we end at 12 meters per second. The acceleration then drops to 0. Remember, what is acceleration on a velocity time graph? It is the slope. So the slope is 0. So did she fall down? Well, to fall down, she would have to slow down, right? This graph would instead decrease. So it can't be that. For her to slow down, she would have to have a negative acceleration vector. So that can't be true. And so it's instead that she continues to move at her top speed. So something where in society we really don't quite use the word acceleration just right. Having the acceleration drop to 0 means not that she stopped, but that she is moving with constant velocity. All right, another check here. If a boat has a velocity of negative 12 meters per second and speeds up, what is the direction or sign of the acceleration? So remember that the acceleration will always match in sign with the change in velocity vector. So if the velocity of the boat is to the left, or in the negative direction, and this value is going to increase, again, velocity time graphs are really helpful. We start at negative 12, and the value of that negative number increases, then we have a negative slope, and we must have a negative acceleration. Okay. Now that we've talked about acceleration, we're ready to introduce our first Pies method. So these Pies methods are a means to solve physics problems and deal with the fact that physics can feel very challenging because every problem is different. The method is the same, but setting up and knowing then how to work with your concepts will require different techniques for each problem. So this Pies method, for those who have had them before, you'll be familiar with what this is, and you can move to whatever slide is relevant for you. But for those who have not, it means that you start by drawing a picture with labels of knowns and unknowns. You always should do this. This is how you think through a problem. You then model the information for the I step, and that will change with each unit. Each topic in physics has a different modeling method. From your model, you develop your equation. You solve for the unknown without numbers, and then you substitute numbers for a solution with units. Please trust me on the importance of solving without numbers first. As you get further along in math and science, numbers start to disappear, and it is really important that you are comfortable using the tools of math and science with symbols and not needing to have numbers to think that you've solved something. All right. The key for kinematics, for this I step, for this modeling the information step, is that you start by making a velocity time graph. The velocity time graph provides you with everything that you need to solve the kinematics problem. It also will help us set the foundation for what we need for calculus. The velocity time graph is very valuable because remember we talked about, let's say I have a graph that looks like this. The area here, we say from the curve to the x-axis, but I'm going to say from the line of the graph to the x-axis equals the change in position, and the slope equals our average acceleration. And with those tools, we can then solve any problem that we have by being able to work with these two things, area and slope. So to build on these two important facts, the first is to remember that the slope is the acceleration. And it's also important to point out that this is the average acceleration and the slope must be constant. Right now we don't have the tools to deal with a non-constant slope. To have a non-constant slope, we'd have to use a tool called a derivative. And to find the area, we'd have to use a tool called the antiderivative, or what's also called integral. So for the thing about kinematics, the reason why we don't need that calculus yet is because in kinematics the acceleration is constant, which can actually be a pretty good approximation for a variety of different things that we'll talk about more when we get to freefall. The other thing for this velocity time graph, besides what is the slope here and that it is the acceleration, is that the area, remember we've now talked a few times, is the displacement, the change in position. Let's say that we wanted to find the distance. The distance is the absolute value. So if I had a graph that was instead negative, I would have a negative displacement, but I would have a distance value that's just a number, right? And it would need to be the absolute value of that displacement. The good news is that the area of these graphs are always made up of geometric shapes because the acceleration is constant. When the acceleration is not constant, we start to think about how do we fit these geometric shapes in to get a good approximation, which is what you start to talk about when you talk about Riemann sums, as this idea of making better and better approximations of that area. And I'll leave a discussion of that to what you do in your calculus class. It's not something we need right now. All right, let's keep talking about this just a little bit more. Let's talk about how we find these areas. So the most simple velocity versus time graph would be a velocity versus time graph where the velocity is constant. In that case, the area would be simply the velocity times the time interval, base times height. Sometimes, though, we have things a little bit different where we start from rest, right? And in that case, we have a graph that is now a triangle. To find the area of that, we'd do 1/2 of the base, which is the time interval, times the height, which is this v final. Now let's talk a little bit about this. What this really is 1/2 of v final plus that v initial times delta t. But because v initial is 0, it looks as if it's not there in the equation. The reason I point that out is because it becomes relevant for finding the area of a trapezoid shape. Right? For a trapezoid shape, we do 1/2 of the time interval times the two velocity values added together. What is the v initial and what is the v final? The key thing to remember here is that the average velocity, what we are finding here is what equals the change in position over the change in time. So if we instead rearrange this to write average velocity times change in time equals the change in position, the average velocity is what we are finding when we do 1/2 of v final plus v initial. We're adding two numbers together and dividing by the number of things we add together, and we find an average. So we are applying this equation to a graph, but it's a lot easier to visualize and solve when we have a graph. Now let's say that the motion is not always the same, in that look at the last example here, where we have this trapezoid, and then we have a rectangle. When we want to find the total displacement, what you have to do is separate these steps into their individual segments, and then add them together. And that would give us our total displacement and our total distance. The key difference is, for displacement, you keep the positive and negative signs. For distance, you simply add all of the numbers. Think of adding all the absolute values. Right, what we'll do now is do some practice problems to illustrate how to use this method. Right, example problem 1, we have a Tesla Roadster that can accelerate from 0 to 60 miles per hour in about 2.1 seconds. We want to figure out, assuming a uniform acceleration, what is the displacement after 2.1 seconds. So remember, the first thing we do is we always draw a picture. And the picture needs to label all of the things that we know. It's a way for us to simply organize information. So it starts from rest, meaning that v initial is 0. And v final, we're told, is about 27 meters per second. We know the time interval is 2.1 seconds. The things we don't know are the acceleration, and we don't know the displacement. So this helps us to organize what do we know and what do we not know. Now, the problem then asks us to find what is the displacement. So first thing we do is make a VT graph to model the information. On this VT graph, what I want to do is show that I start from rest. I have uniform acceleration. Now, we're not told if it's positive or negative, so always make your life easier. We'll assume positive direction. And we go to a v final that is equal to 27 meters per second. And we know that that time is 2.1 seconds. To find the displacement then, after we've modeled this information, we can say that the acceleration here is unknown and the area is unknown. The way that we want to solve now is to remember our two bits of information. The displacement's the area, and if we need it, the acceleration is the slope. Our goal is to find the displacement, so that's what we'll start with. The area, this is a triangle, so it's 1/2 the height, which is v final, times the base, which is the change in time. And you ask yourself, do you know these things? Do you know v final? We do. Do you know the time? We do. So the displacement then, this is when we solve. I already have the equation solved for the thing I want, equals 1/2, and now I can put in numbers of 27 times 2.1 seconds. And that would be how we would obtain our answer for how far does this go. So we then find that the Roadster travels 28.4 meters. A note on sig figs. For the AP exam, they really are not picky about sig figs as long as your answer is not sort of an endless number and it's sort of reasonable. So technically for this problem, I only have 2 sig figs. I'd need to write 28 meters. I like to have that 28.4 just to be a little bit more detailed, but you wouldn't lose a point if you wrote 28 versus 28.4. Number 2. A car is traveling at 15 meters per second and then accelerates constantly at 5 meters per second squared for 3 seconds to pass a car. How much distance did the car travel while accelerating? So remember, first, our picture step, the car starts here, traveling with v initial of 15 meters per second. In a time span of 3 seconds, the car then speeds up at an acceleration of positive 5 meters per second squared. The displacement is unknown, and v final is unknown, though you're probably thinking I can do it in my head. right? V final, the change in velocity is the acceleration times the time. So 5 times 3 would be 15. So we would have a new velocity. We'd have a change in velocity of 15, which means that if we started at 15, we go to 30. So this would be 30. But technically, we'll label this as an unknown since it wasn't directly given to us. To model the information, then, we need to make our VT graph, remembering that we are not starting at 0 this time, we're starting at 15. So the car will assume instantly starts accelerating in this problem, and we end at this V final up here. And to end at that V final up here, it takes a total of 3 seconds. And we're asked to find the displacement. So remember that the displacement is the area, and if we need to incorporate it, the acceleration is the slope. Okay, so let's build the equation for that area. The displacement is the area, which is going to be 1/2 of V final plus V initial, right, because this is now a trapezoid shape, times the change in time. So notice here that we don't know what is V final. Technically, we need to incorporate the acceleration. So the acceleration, remember, is equal to V final minus V initial over change in time. So the way we solve these problems when it's not just one simple step is to solve and substitute in the other equation to finish our first equation. Meaning that I want to solve this acceleration equation for V final without putting numbers in. Avoid the numbers to start. So V final is going to be equal to acceleration times change in time plus V initial. And what I can do is now substitute that into the first equation. So now I can say, okay, the displacement here is equal to 1/2 of the acceleration times the change in time plus V initial, right, that's all of what V final is, plus V initial, all times delta t. And we could simplify this a few different ways, which I have to do over here, a little out of space. So this would be 1/2 acceleration times delta t squared, plus, I have these 2 V initial times a 1/2 gives me 1 V initial, so plus V initial delta t. Now, if you're doing the textbook reading, you might notice that this is what the textbook calls a kinematics equation. Do not use the kinematics equations, please, especially since you guys really are quite adept at math. You might go, oh, I have an equation, it applies, I'm going to use that. It's really easy, it's really straightforward. But the goal here is to help you understand this kinematics process and to understand the mathematics principles behind them. If you do this, this will help you succeed in this course far more than if you just memorize an equation. So I have derived one of the kinematics equations, but I'm not simply going to write it down. We'll talk about saving time for the AP exam and what you can cut corners on then, but for now we really want to strive for understanding, not memorizing. Anyways, we have the equation now that we want. To find this displacement, I can do 1/2 times the acceleration, right, times the time squared, plus the V initial, which is 15, times that time of 3. So notice that 15 times 3 is actually the area of the bottom section, and that 1/2 AT squared represents the area of the top section. The rectangle there has an area of 45 meters. The triangle has this area of 22.5 meters, and so together they add up for a total displacement of 67.5 meters. That's another Pie's method problem. Let's do another example. An example problem here where we have to infer some things that are not explicitly stated, which is a really important skill when you're dealing with college-level physics problems. We're told that we're driving through town at 12 meters per second. So for this car, our V initial is 12 meters per second. And a ball rolls out in front. We want to apply the brakes and slow down with an acceleration of 3.5 meters per second squared. We're asked how far do we go before stopping. Now a few notes, right? We're slowing down, so if this velocity vector is positive, I need my acceleration to be negative. Now, if you just write these two bits of information, you're going to think to yourself, I don't think I have enough information to solve this problem. And you have to infer something, right? Infer what is meant by stopping. Stopping implies that v final is 0. I don't know my displacement, and I don't know my time interval. But these are things that I can find now that I have the three pieces. So let's model the information. I start at 12 meters per second, and I go to 0. That's v final, this was v initial. The slope here is my acceleration, and it is a negative 3.5 meters per second squared. So the first equation, the displacement, which is what I want, is 1/2. It's the height, which is v initial, times the time. The problem is I don't know the time. When you don't know one of these variables, what you always want to remember is you go to the acceleration equation, which is v final minus v initial over the change in time. That's the average acceleration. So what we want to do is solve for the thing we need, which is time. And that's what we want to get rid of, right? So delta t is v final minus v initial over a. Now v final is 0, so this is technically negative v initial over a. And that's what we will substitute in here, is that the displacement is 1/2 of v initial times negative v initial over a. And now we are ready to substitute our numbers. We have 1/2 times 12 times a negative 12, and this is where the negative sign is important, right? Because the acceleration is also negative, and so the two negatives will divide out. And this will give us our displacement that the car travels about 20.6 meters. And that's our answer. Okay, let's do another example with a different sort of... We are given a situation. We have a roller coaster that starts at rest on top of a hill, and it accelerates with constant acceleration down to the bottom, 25 meters long, and the time interval is 3 seconds. Again, we have to infer something here, right? What we have to infer is that v initial is 0. We don't know v final, but that's what we want. That's the thing we're trying to find. And we also don't know the acceleration. To model this information on a VT graph, we'd start from rest and increase our velocity with a constant rate, and the area is 25. So remember, we always start with this displacement equation. It's the area of this triangle, which is 1/2 the v final we don't know, times the change in time. So you ask yourself, do we know the displacement? We do. Do we know the time? We do. So what we need to do is solve for v final. V final, if I move the 1/2 over, is twice the displacement divided by the time. So that will be 2 times 25 meters divided by 3 seconds. And that will be our answer for our final velocity, right? So that would be 50 divided by 3. What is that? 16, just a little bit over 16 meters per second. All right, let's move on to question number 5. We are driving through town at 12 meters per second when a ball rolls out in front, and we apply brakes and it takes 20 meters to stop. Assuming we slowed down at a constant rate, what is the acceleration needed to stop with no room to spare? So this problem is actually a modification of the earlier problem, where again we know the initial velocity is 12, but this time I've given you instead the displacement constraint of 20 meters. We don't know the acceleration, and we don't know the time. We do know that the stopping speed, right, v final, must be 0, so that's something we're inferring. To make the VT graph, assuming we have no reaction time, we have a graph like this. Right? If we did have a reaction time, the graph would look like this as we take some time to think about stopping. But we don't need to worry about that for now. What acceleration is necessary to stop with no room to spare? So I always like to still start with the displacement equation, which is 1/2, this time v initial times delta t. And then for the acceleration, remember is v final minus v initial over the change in time. So to find the acceleration, the key is we need to know v final, which we do, it's 0. We need to know v initial, which is 12. And we need to know the time, which we unfortunately do not know. So that's where we come to the first equation, and we solve for time. So the change in time is going to be equal to 2 times the displacement divided by that initial velocity. So what we're going to do now is substitute that in to our equation. So the acceleration is equal to negative v initial divided by 2 delta x divided by v initial. So rewriting that into something that looks a little bit prettier is negative v initial times v initial over 2 delta x, or negative v initial squared over 2 delta x. Now this again comes from one of those kinematics equations in your textbook, and again I want to emphasize, use the problem-solving method to help you understand. Don't just jump to an equation. I won't give full credit if you just jump to an equation. Work through the thinking process. All right, so we have then a negative of the 12 meters per second squared. It's important we have a negative sign because we are slowing down, right? And then 2 times 20. So we're doing 144 meters squared seconds squared with a negative sign, right, divided by this 40 meters. And that gives us our acceleration value, negative 3.6 meters per second squared. Okay, so that's 5 examples of how to use this Pies method process. The practice problems now will help you work through this process more fully and help you to become more comfortable with it. It will be really important as we approach solving a particularly important part of kinematics, which is free fall motion, and that will be our next topic of discussion. Thank you for watching. If you have any questions, feel free to send me an email. Otherwise, have a great rest of your day.